Okay, so this problem was really interesting, and it kind of harkened back to a lot of the work that we did last semester involving balancing, using the conservation of energy and doing energy balance equations. And so basically what the problem outlined was two beads that were near each other, and I guess we were just assuming that they were floating in space and there were no other forces acting on them except for the fact that one was charged to -5 nanocoulombs, the other one was charged to -10 nanocoulombs. Now, obviously they're going to repel each other with some amount of force, and the way that you find the final velocity of each bead is by, first, well, I just drew it, set it up here. One weighs 15 grams, one weighs 25 grams, and they're 0.12 meters apart. Anyway, the way that you eventually find the final velocity of each bead is by basically by using the law of conservation of energy to set up an equation that relates the kinetic energy initial plus the potential energy initial and the kinetic energy final and the potential energy final. Basically what you find is that because they're not moving when they're starting, the kinetic energy initial is 0, and because you want to know their final velocity, when they are moving at their final velocity, which is going to be their highest velocity, their potential energy will be 0. So you can essentially say that the potential energy initial is equal to the final kinetic energy, which is final. So yeah, this is actually very similar to the equations that we did last semester in 207 regarding gravity, and like how high you lift something up is how much potential energy, gravitational potential energy that it has is directly dependent on height, but instead of gravity, we're using electric field and the forces that have to do with electric field. So basically, we know how to find the potential U, that's K, Q1, Q2 over R, and we learned that relatively recently. So we can find U, the potential energy. It's measured in joules. I don't know why I didn't write joules, but it's potential energy is equivalent to 3.75 times 10 to the negative 6 joules. And we can use that figure to find the kinetic energy final. So we also know that kinetic energy is equal to 1/2 mass times velocity squared, and we can just kind of manipulate this, multiply both sides by 2 and divide by mass, and then you have to get rid of the squared, so you square root. So you eventually end up with the velocity final is equal to the square root of 2 times the potential energy initial over the mass. And also, I just wanted to make a reminder, the mass is different for both of the beads, but the potential energy is the same because they're floating in space and they're near each other. They both have a charge on them. They're both going to have the same potential energy. In fact, they're both going to be pushing away with the same amount of force. The reason that their final velocities are different is because one has more mass than the other one. So even though they have the same potential energy, they're not going to have the same final velocity because one weighs 25 grams and the other one weighs 15 grams. So obviously the one that weighs less is going to be traveling faster at the end than the one that weighs more. And that actually, if you plug in the numbers, which I did, is what I found. Velocity final for bead 1, which is the one that weighed 15 grams or 0.015 kilograms, is 0.023 meters per second, and for bead 2 it was 0.017 meters per second. I just said that's exactly what you would expect because bead 2 weighs more, it has more mass than bead 1, and these velocity final 1 and velocity final 2 are the final velocities for both beads.